Hello, good morning to everybody. Today, let us see lecture number 8, chapter number 5. Last time, we already seen how to find a derivative of parametric form, as well as how to find second derivative in case of function is given in parametric. Today, very simple sums we are going to see that example of derivative based on second derivative. Okay. Let us see here. What is given? Find d2y by dx square if y is equal to x cube plus 10. Here ordinary form is given. They want in terms of x. Y is equal to x cube 10x is given to us. Differentiate once again, derivative. Here y is equal to x cube 10x. So, what is dy by dx? D by dx of x cube plus 10x. That is equal to d by dx of x cube plus d by dx of 10x. Very simple form. Some function raised to n, 3 times n times some function raised to n minus 1 d by dx of some function. 10 of some function. 6 square some function d by dx of some function. So that is equal to 3x square plus x square x. That is our dy by dx. Once again differentiate. And therefore d by dx of dy by dx is equal to d by dx of 3x square plus x square x. So what we get here? And therefore d2y by dx square is equal to 3 times d by dx of x square plus d by dx of x square x. That is equal to 3 d by dx of something square, 2 times something d by dx of something, 2 times 6 something into d by dx of something. What happens? That is equal to 6x plus 2 6x, 6 something, 6 something, 10 something, d by dx of something. So that comes out 6x, 2 times 6 square x into 10x. Yes, this is the okay. Yes, see here. Next, what we want? Y is equal to a sin x plus b cos x. Then prove that d2 y by dx square plus y is equal to c. A and b is arbitrary constant. Later on we are going to see that this one is the differential equation of this function. That thing we are going to see in chapter number 8. But today just how to find a second derivative or some relation based on second derivative. See, a relation is there. So let us see y is equal to a sin x plus b cos x. Y is equal to a sin x plus b cos x. So differentiate with respect to x, d by dx of a sin x plus b cos x. That we can say that this one y1 was. You can write dy by dx, y1, y double, y dash, whatever. But it is easy to write in terms of y1 and y2. So write y1. At last, whatever they want, convert it to that form. If they want in terms of dy by dx, dy by dx, so then at last put it into that form. But for simplicity, if it is y1, then it is easy to write. So I am writing it. So a constant outside d by dx of sin x, b constant outside d by dx of cos x, sin of some function, cos of some function, d by dx of some function, plus b cos of some function minus sin some function d by dx of some function. So what we get, y1 is equal to a cos x minus b sin x. Once again differentiate it. D by dx of y1 is equal to d by dx of a cos x minus b sin x. But the derivative of y1 is y2 or y double s or d2 y by dx. So y2. A constant, take it common, a cos x minus b constant, so take it common, d by dx of sin x. Okay. Now let's cos something minus sin something, d by dx of some function minus b sin of some function, cos of some function, d by dx of some function. That is 1. This is also 1. So therefore, what we get, y2 is equal to, take minus sign common because there is minus here also minus. A sin x plus b cos x. See? What is that? Y. So that is equal to minus. And therefore y2 plus y is equal to 0. Or you can write y double s plus y is equal to 0. Or you can write d2y by dx squared plus y is equal to 0. Yeah? Yes. Next one. Answer. Y is equal to 3 e raised to 2x plus 2 e raised to 3x. Then prove that this thing. That is equal to 0. Right now I am giving this sum for homework. So this type of sum we are going to put next to after 1 or 2 slides. Here, in place of 3 I am going to take a e raised to mx plus b e raised to nx. M is 2, n is 3, b is 2, a is 3. Clear? So, in general, this sum is given to us how to find derivative. That thing we are going to see next slide, next 1 or 2 slides. After 1 or 2 slides. So, let us leave for you this one. Let us see this one. Here, sin inverse x is given. See. Y is equal to sin inverse x or y is equal to cos inverse x, then above. I am going to prove it for square, then what happens? See. This one is also for you. Let us solve this one. Sin inverse x whole square. This implies 1 minus x square y2 minus x y1 is equal to 2. That thing we want to show for this sum. Here only sin inverse x is given. If I solve this one, then you are able to solve this thing. So this is just I am showing this one. Same result for cos inverse also there. Y is equal to cos inverse x whole square, then also same result is there. Clear? So I would like to solve this one. See. What is given? Y is equal to sin inverse x whole square. Differentiate with respect to x on both sides. dy by dx is equal to d by dx of sin inverse x whole square. And this is in our routine case, that is y. What is d by dx of some function? Square. Sin inverse x whole square means what? That is equal to 2 times some function d by dx of some function. That is 2 sin inverse x, sin inverse some function 1 upon under root 1 minus some function square d by dx of some function. So what we see, and therefore y1 is equal to 2 sin inverse x over under root 1 minus x square. See, whenever inverse trigonometric functions are given to us, then find out first derivative in this way. Then for second derivative, we are not going to apply division rule. Then one question arises, how we avoid division rule? Yes, take denominator quantity on left hand side. Here, see here. And therefore, under root 1 minus x square y1 is equal to 2 sin inverse x. Here, this says that there is no need to apply division rule. Once again, whenever we want derivative of inverse trigonometric functions, second derivative of inverse trigonometric functions, or any form is given to us, but if after obtaining first derivative, if anything is common to in denominator quantity, take it on left hand side. Then second rule, second important step. After taking denominator quantity on left hand side, if only single term is on right hand side, then square on both sides. Squaring on both sides. When if right hand side consists single term. Clear? Other than single term is given to us, what we are going to see? That thing we are going to take one more example after completing this example. In that case, on right hand side we get two terms. So we are not able to take square on both sides. Squaring only when right hand side, this side, consists single term. Single term. Here. So here it is single term is there. So we are taking squaring on both sides. 1 minus x square by 1 square is equal to 4 by. Why? Because sin inverse x whole square is equal to y is given. Now differentiate on both sides with respect to x. And therefore, product rule 1 minus x square d by dx of y1 square is d by dx of 1 minus x square, 4 outside, d by dx of y, dy by dx, that is y1. So what? And therefore, 1 minus x square, y1 something square, 2 times something d by dx of something, y1 square derivative 1 is 0 minus 2 times something d by dx of something, that is equal to 4y1. Yes, very simple. So therefore 1 minus x square 2y1 y2 minus 2x y1 square is equal to 4y. Whenever you are squaring on both sides, then definitely it is divisible by 2y1. Dividing by 2y1 not equal to 0. What we get? 1 minus x square y2, 2y1 minus xy1 is equal to 2. And see, this thing we want to show. See? We can prove it. Cos inverse, no problem. Only minus sign is there. Here minus 2 cos inverse. If you square it on this side, then you get 4 cos inverse x square. Same relation you get in that example. But only single term is given, then we have to take square. If other than single term is given, then what we have to do? Let us see for this one more expression. Y is equal to sin inverse x whole square plus b sin inverse x plus c. Once again, this implies same quantity. 1 minus x square y2 minus x y1 is equal to 2. That thing we want to show for this example. Y is equal to sin inverse x whole square plus b sin inverse x plus c. Now differentiate it. dy by dx is equal to d by dx of sin inverse x whole square plus b sin inverse x plus c. What we get here? We get here y1 d by dx of sin inverse x whole square, b outside, d by dx of sin inverse x plus derivative constant term is 0. And therefore, y1 is equal to 2 times some function d by dx of some function. Okay. b into d by dx of sin inverse x. Let me differentiate in seconds. 2 sin inverse x. Sin inverse some function 1 upon under root 1 minus some function square into d by dx of some function. B 1 upon under root 1 minus some function square d by dx of some function. See, this is our y1. Now under root 1 minus x square take on left hand side. Derivative quantity taken on left hand side. What we get here? 2 sin inverse x plus b. See here, 2 terms are there. Then we are not going to square on both sides. Then differentiate directly. See. And therefore, d by dx of under root 1 minus x square y1 is equal to d by dx of 2 sin inverse x plus b. And therefore, root 1 minus x square d by dx of y1 is d by dx of root 1 minus x square 2 times d by dx of sin inverse x plus d by dx of the constant term. We can put it 0 also. And therefore, under root 1 minus x square, what is derivative of y1? It is nothing but y1. Plus y1, root something, 1 over 2 root something, d by dx of something, 2 times, sin inverse something, 1 upon under root 1 minus something square, d by dx of something, that is x, and this is 0. Plus 0. What do you get here? And therefore, under root 1 minus x square y2, derivative of 1 is 0, y1. Derivative of minus x square 2 times x into dx by dx over under root 1 minus x square. Yes. times under root 1 minus x square. What we get here? Under root 1 minus x square, 1 minus x square by 2 minus xy1, 2xy1 under root 1 minus x square is equal to 2. Here 2 is there, so that 2 get cancelled. Sorry, no. Clear? Yes. These 2 get cancelled. Take root 1 minus x square on both sides, LCM on both sides and cancel it. What we get? 1 minus x square by 2 minus xy1 is equal to 2. And that thing you want to prove. See? Now in place of sign, they can take cos inverse also. Y is equal to cos inverse x whole square plus b cos inverse x plus c. Okay. On same line you can see that thing also. So let us see. Sin inverse x only or cos inverse x only, then we can solve likewise this one. Sin inverse x whole square, cos inverse x whole square. If single term is there, then squaring on both sides. If single term is not there, then we have to differentiate directly for the second derivative. Okay? Yes. Let us see next slide. Yes, very simple thing. Find second derivatives of the functions. Okay. Simple for you, for you, for you, for you, for you. 1 to 6 for you. Okay. Let us see. E raised to 6 cos 3, then tan inverse 6, and then log x, what? Sin log x. Let us consider log x, and this one is also for. First of all, I would like to take 8. Y is equal to tan inverse x. What we get? dy by dx is equal to d by dx of tan inverse x, tan inverse something 1 upon 1 plus something square, d by dx of something. So what we get? y1, we get 1 upon 1 plus x square. So if I take d by dx of y1 is equal to d by dx of 1 upon 1 plus x square. Here what we get? Y. 1 upon some function minus 1 upon some function square d by dx of some function. So minus sign derivative of 1 is 0. 2x into dx by dx over 1 plus x square whole square. Derivative of 1 is 0. Something square is this one. So what we get? That is equal to minus 2x over 1 plus x square. Next, let us consider y is equal to log x. dy by dx is equal to d by dx of log x. And therefore y1 is equal to 1 over something, log something, 1 over something. D by dx of something. And therefore y1 is equal to 1 over log x into, yes, 1 by x into d by dx of x. So, and therefore what we get? y1 is equal to 1 upon x log x. What we get? y1 is equal to 1 upon x log x. So differentiate it. d by dx of y1 is equal to d by dx of 1 upon x log x. This one is y2. 1 upon something minus 1 upon some function square. Whole square. Into d by dx of some function. So that is equal to what? Minus 1 upon x log x whole square. X is the product. d by dx of log x. Log x in d by dx of x. As it is. Yes. So what we get? Minus 1 upon x log x whole square. X is the derivative of something, 1 by something, d by dx of something. And that is log x. So what we get? This one is 1. So minus of 1 plus log x over x log x whole square. This is the second derivative. Now combination of, see, already seen this one, log x tan x. Now let us consider y is equal to e raised to 6x cos 3x. E raised to 6x sin 5x is there. Here x cos x, here x cube cos. Here product rule, here product rule, here product rule, and here product rule. Remaining single terms are there, and these are the composite forms. You already seen. Let us take e raised to 6x cos 3x. Y is equal to e raised to 6x. Y is equal to e raised to 6x cos 3x. See. Find out second derivative. And therefore dy by dx is equal to d by dx of e raised to 6x cos 3x. What we get? Product. E raised to 6x d by dx of cos 3x plus cos 3x is it is d by dx of e raised to 3x. So on left hand side what we get? y1 is equal to e raised to 6x cos some function minus sin some function d by dx of some function cos 3x is it is e raised to some function. E raised to some function d by dx of some function. So what we get? y1 is equal to minus 3x is 3 minus 3 e raised to 6x sin 3x plus what is d by dx of e raised to 3x? 3x is 3 e raised to sorry. Here also mistake is there. Here 6 is there. So e raised to 6x d by dx of 6x. So here what comes out? 6 e raised to 6x cos 3x. Okay. This is the first derivative. Now see second derivative, and therefore d by dx of y1 is equal to d by dx of minus 3 e raised to 6x sin 3x plus 6 e raised to 6x cos 3x. So what we get here is nothing but y minus 3 times d by dx of e raised to 6x sin 3x plus 6 times d by dx of e raised to 6x cos 3x. And therefore y2 is equal to minus 3. Apply product rule. E raised to 6x d by dx of sin 3x. Sin 3x as it is, d by dx of e raised to 6x plus 6 e raised to 6x as it is, d by dx of cos 3x plus cos 3x as it is, d by dx of e raised to 6x. We have to apply product rule. So that is equal to minus 3 e raised to 6x. What is d by dx of sine some function? Cos some function, d by dx of some function. Sin 3x is e raised to some function, e raised to some function, d by dx of some function. First bracket complete. Now what is second bracket? 6 e raised to 6x cos some function minus sin some function d by dx of some function plus cos some function is given e raised to some function d by dx of some function. Yes? Yes. So that is equal to, this one is 3 and here 3 is there. So minus 9 e raised to 6x cos 3. Here 6 and here minus 3 is there. Minus 18 e raised to 6x sin 3. Minus 3 6. That is minus 18 e raised to 6x sin dx. 6 36 plus 36 e raised to 6x cos 3. So now you can see that 18 minus 36 e raised to 6x sin 3x. 36 minus 9, 27. 27 e raised to 6x cos 3. So this is the second derivative of derivative. Okay? Yes. See, for this part. Now, all of you are able to solve remaining sum, how to find second derivative. Next slide. See here. See, we already seen this form. Y is equal to a sin x plus b cos x. This general example, what is seen? Your particular example is that a is equal to minus 3 and b is equal to 5 is given to us. On same line we have to do it. So I am leaving this one for you. Next. See. Yes, interesting part. See, I already told that a is equal to 2, a is equal to something, b, m is equal to 2, n is equal to 3. Likewise, that particular example is given here, in general example is given. So let us see one by one. Interesting question thing is that here it is given that y is equal to cos inverse x is given. Find d by dx in terms of y alone. It should be in terms of y. You can see in both ways. Y is equal to cos inverse x is given, and therefore cos y is equal to x is there, and therefore d by dx of cos y is equal to d by dx of x. We can write it cos some function minus sin some function d by dx of some function is equal to 1. So what we get? We get dy by dx is equal to minus 1 upon sin y. That is minus cosec y. So what is d by dx of dy by dx? Is equal to d by dx of minus cosec y. So what we get here? d2y by dx square is equal to minus of d by dx of cosec y. And we know that, see. And this one is said to be y. Yes? Minus sin as it is. Cosec something, cot something, d by dx of something, that is y. So that is cosec y, cot y. What is dy by dx? Minus cosec y. So that comes out minus cosec square y into cot y. So this is the y in terms of y. See what they want? Find dy by dx the second derivative in terms of y. Here they are writing a is equal to, see, 3 cos log x, 4 sin log x. I am going to solve in general. Y is equal to a cos log x plus b sin log x. Same result is that. Yes. So let us see that one. Y is equal to a cos log x plus b sin log x. Let us see this one. Once again, we need to differentiate with respect to x on both sides. So what we get? dy by dx is equal to d by dx of a cos log x plus b sin log x. And here can I write is a y1? Yes. As it is constant, so take it outside. D by dx of cos log x plus b as it is, take it outside. D by dx of sin log x. Yes or no? Yes. So therefore y1 is equal to a cos of some function minus sin of some function d by dx of some function, okay, plus b sin of some function cos of some function d by dx of some function. So what we get? Therefore y1 is equal to minus a sin log x. What is log some function? 1 upon some function d by dx of some function. B cos of log x, log some function, 1 by some function d by dx of some function. See, x is there. So take it on left hand side. X y1 minus a sin log x plus b cos log x. Now differentiate with respect to x once again. So what we get? Therefore d by dx of a y1 x y1 is equal to d by dx of minus a sin log x plus b cos log x. So here apply product rule. x as it is d by dx of y1, y1 as it is d by dx of x minus a d by dx of sin log x 1 into b d by dx of cos log x. So what we get here? Therefore, x y derivative of y1 is y plus this one is what? y1 because it's 1 minus sin a sin something cos something or some function d by dx of some function. Now cos some function minus sin some function d by dx of some function. Okay? So therefore x y2 plus y1 is equal to minus a cos of log a. It is log some function 1 by some function d by dx of some function minus e sin log x into 1 by some function d by dx of some function. Once again x is there, take it on left hand side. What we get? X square y2 plus xy. Xy is equal. Here minus and here minus and take it common. A cos log x plus b sin log x. Please see, what is this one? It is nothing but our y. And therefore x square y2 plus xy1 is equal to minus y. See. A cos log x plus b sin log x is equal to y. So what we get? X square y2 plus xy1 plus y is equal to 0, and that we want to prove. Okay. Now dear friends, all of you are able to solve this one. All of you are able to solve this example. Y is equal to 3 cos log x plus 4 sin log x. On same time, constant does not play any role. Okay? Yes. Now let us see this one. In general question is given. Y is equal to a e raised to mx. Y is equal to a e raised to mx plus b e raised to mx. Yes or no? Let me clear this thing. Yes. This is given. Then what we want? Y2 minus m plus n into dy by dx plus m and y is equal to 0. Exponential form is that. Say result number 1. Now differentiate it. Dy by dx is equal to d by dx of a e raised to mx plus b e raised to nx. Clear? So you can say that y1 also, no problem. A as it is d by dx of e raised to mx plus b as it is d by dx of e raised to nx. So that is equal to a e raised to some function into d by dx of some function b e raised to some function d by dx of some function. What is mx? N. A n e raised to mx b n e raised to nx. And that is our y1. Say result number 2. Find out one more derivative. And therefore d by dx of y1 is equal to d by dx of am e raised to mx ba e raised to nx. And therefore this is nothing but y2. am d by dx of e raised to mx, bm d by dx of e raised to mx. Why? Am is constant, bm is constant. So we can take it outside. So that is equal to am e raised to some function, e raised to some function, d by dx of some function, plus bm e raised to some function, e raised to some function, d by dx of some function. So what we get here? Mx is a. So am square e raised to mx, bn square e raised to nx. And this is over by 2. Say result number 3. Now what we want to prove? And therefore, what we want? We want d2y by dx square minus m plus n into dy by dx plus mn1. Let me see. Plus mn1. d2y by dx square minus m plus n into mn1. That is equal to y2 minus m plus m into y1 plus mn1. What is y2? am square e raised to m, bn square e raised to n, minus m plus n. What is it? y1 am. am e raised to mx, bn e raised to nx, plus mn y. What is y? a e raised to mx plus b e raised to nx. a e raised to mx plus b e raised to nx. Yes, now we have to simplify. See. Let us see. Here what we get? am square e raised to m, bn square e raised to n. First of all, multiply by m. Minus am square e raised to mx minus bmn e raised to nx minus amn e raised to mx minus bn square e raised to nx plus mny. So mn a e raised to mx, mn b e raised to nx. Now you can see that this one is cancelled with this thing. This one is cancelled with this one. This one is cancelled with this one. And this one is cancelled with this one. So ultimately what we get? See. And that thing we want to see. Okay. Now see, these are the question of 4 marks are there. Okay? Yes. Next one. See here. Very simple form is that. So I'm not going to solve this one. 500 into 7 e raised to 7 is 600 into minus 7 into e raised to minus 7 is, that is the your divider. Once again differentiate it. 49. No problem. Or you can say that in this also. Y is equal to a e raised to x plus b raised to minus x, then this one is equal to, here only y is there, so divided by dx it comes out y. Here particular value is taken, so I am leaving this one for you. Clear? Let us see this one, very important. Then this thing is also there. See? See? E raised to y into x plus 1 is equal to 1. We want to prove some relation. d2y by dx is equal to this one. And therefore x plus 1 is equal to 1 upon e raised to y. So we can write x plus 1 is equal to x plus 1 is equal to e raised to minus y also. Take d by dx on both sides. X plus 1 is equal to d by dx of e raised to minus y. And therefore what we get here? D by dx of x plus d by dx of 1, d raised to some function, d by dx of some function, 1 by 1. So here you get 1 is equal to minus e raised to minus y divided by d. So please tell me what is d by dx? Minus 1 upon e raised to minus y, that is minus e raised to y. Divided by dx is equal to minus e raised to y. No. Once again differentiate it. And therefore d by dx of d by dx is equal to d by dx of minus e raised to y. What we get here? d2y by dx minus of d by dx of e raised to y minus e raised to y d by dx of y. So what we get? Minus e raised to y into minus e raised to y divided by dx is minus e raised to y. So what we get? Minus e raised to y whole square is nothing but d by dx whole square. Yeah, that thing we want to prove here. See? Yeah? Yeah. Now let us see y equal to tan inverse x whole square is given to us. Then show that this thing. See? What is given? Y is equal to tan inverse x whole square is given. See, always seen y is equal to sin inverse x whole square. Same line for cos inverse x whole square. Y is equal to tan inverse x whole square or cot inverse x whole square. One and same thing. See. What we get? dy by dx is equal to d by dx of tan inverse x whole square. So, what we get here? y1 is equal to 2 times some function d by dx of some function. So therefore y1 is equal to 2 tan inverse x, tan inverse some function, 1 upon 1 plus some function square d by dx of some function. So therefore y1 is equal to 2 tan inverse x over 1 plus x square. I already told you previously, whenever we want second derivative of inverse trigonometric function, then after obtaining first derivative, whatever may be denominator quantity is given to us, take it on left hand side. See, so equal that thing. And therefore what we get? 1 plus x square y1 is equal to 2 tan inverse x. Same time, same time we seen the second rule also. And whenever on right hand side single term is there, you can square on both sides. If other than that is two terms are given to there, then no need to square it. Then we can't square it. No need to means no. Sorry. We can't square it, we have to differentiate directly. Here also you can differentiate directly, no problem. Clear? Yes, let us see in this way what is also possible. So differentiate directly, that thing is also possible. 1 plus x square into y1 is equal to d by dx of 2 tan inverse x. And therefore 1 plus x square as it is d by dx of y1 as it is d by dx of 1 plus x square. That is 2 times d by dx of tan inverse x. And therefore 1 plus x square is equal to derivative of y1 y2. y1 as it is, or derivative of 1 0. Derivative of x square 2x over 2. Tan inverse some function 1 upon some function square into d by dx of some function. Now 1 plus x square take LCM and get here 1 plus x square whole square y2 plus 2x is there. 1 plus x square y1 is equal to 2. That thing we want to prove. Yeah. Yes, dear friends. Yes. In second lecture we are going to see mean value theorems. Today we have already seen how to find a second derivative. Clear? So thank you dear friends.